Actually, we're not live, but we're recording. Okay. So today, what are we on? Lecture 10. So today we're going to do need to put the actual screen share up there. Okay. Yeah, we're going to do something a little bit different today than usual. Today's class is actually mainly going to talk about sort of conceptual ideas as opposed to any sort of implementing anything in R today. And the reason for that is we are going to be talking about one focal area that I've kind of brought up in a couple previous classes, right? Which is these kind of two streams of thought when it comes to building regression models. One focused on predictive outputs and the other focused on inference, and especially as a sort of motivating factor, right? Thinking about causality. So we're going to be talking about that today. And we'll spend a lot more time on prediction in a little bit. So I'm sure folks have heard about this, right? So correlation is not causation. And so if you think back to everything that we've done so far when we've run regression models showing the relationships between our input variables, our x's, and our response variables, our y's, we get these beta coefficients and we interpret them in some ways. But you have to be, very careful in the way that you interpret them, because actually nothing that we've talked about thus far is really discussing causality, right? And so we have thus far mainly been talking about correlations, which is the relationship between two variables, as opposed to causation, where one event is the result of the occurrence of the other event. And the standard to demonstrate causality is actually pretty difficult, okay? And we're going to talk about conceptually how you might start thinking about ways to figure out causal relationships. But going back to some of the examples that we've looked at in the past, right? There was an example where we looked at wages, right? And in that example, we saw that there was a wage difference that was observed between people who are female and people who are male, right? And so is that a correlated relationship or a causal relationship? Correlation, right? So if that were a causal relationship, right, then someone could go, if you were a woman and you were looking for more income, you could go get a sex change, and then you would immediately see whatever that number was, like a $20,000 more higher income, right? But we know that intuitively we can kind of grasp that's probably not the case, right? There's something sort of underlying that. And so understanding all of the things related to how variables are related is kind of step one of thinking about determining causal relationships. I actually don't have this in my notes explicitly, so I'm not sure if I could write the exact definition, but there's something known as a data generating process. And the data generating process is essentially everything related to an outcome, including things that are correlated, including things that are causal, things that might be measured and observed, and all the things that you necessarily might not be able to measure or observe. Okay, and so one nice analogy that I've seen regarding this is if you had like an analog watch, right, with a minute hand, seconds, and an hour hand, the data generating process would be all of the things from, you know, the battery in that watch, all the little gears, mechanisms, and cogs, all the way to the movement of the hands, right? But the things that you can actually observe is only the movement of the hands, right? And so the data generating process includes a lot more beyond what is just observed, okay? Any questions or confusions about that? Okay. I wish I had some way of also seeing my screen. I realize I can't do that at the same time. That's all right. Okay, so let's look at this kind of example. So actually, I'll mention a lot of what I talk about today is derived from a really nice textbook. What is the name of this textbook? 1 second. All right. It's by Huntington Klein. It's called The Effect, An Introduction to Research, Design, and Causality. I'll actually give a link to it on Canvas. It's written in a very sort of understandable way, I think. And if you are really interested in thinking about research design and causality, this is a really good sort of modern textbook to learn about this. Okay, let me jump back over here. So much of the material that I'm talking about today is kind of derived from that. And in one of the chapters, they give this really, sort of clear example that we can look at here. So in this example, you've got a little house over here. Okay, and so there's a couple that lives in this house. We'll say Amy and Abel, and they've got a dog. And one morning they wake up and they find that the dog is sitting outside in the lawn. And so Abel says, "Oh, like, how did this dog get outside? We don't want the dog to escape, and so we need to make sure to latch the little doggy door at their front door," right? And so that night, before they go to bed, Abel goes and he closes the door and he latches the little doggy door and he goes, "All right, great. This way, the dog can't escape." And the next morning, they wake up, dog is nowhere to be found, look outside, he's prancing about in the lawn. Oh, okay, how did he get outside? Okay, well, clearly he did not use the front door. Maybe instead he used one of the side windows. Okay, and so Abel says, well, he must have used the side window. So that night he goes, closes that side window, locks it, and sure enough, the next morning, the dog is outside and roaming about. And so the basic idea here is that he's going to go around and he's going to close and lock all of the little side windows and the little sort of basement area. And he's going to do this until one morning he wakes up and he finally finds out that that the dog actually remained inside the house and that couldn't escape, right? And so there are sort of many avenues that the dog may have escaped from, but the sort of process in which Abel goes around to check specific ways that the dog could get out of the house. So this is the process known as identification. Okay. So identification is the process of figuring out what part of the variation in your data answers your research question. Okay, and so what was the research question in this particular case?
Is the dog getting out?
Yeah, how is the dog escaping the house, right? And so by closing avenues of escape, we are identifying the answer by controlling every possible explanation. So it's actually not the case that you can really make any deductions about the cause and effect until you've kind of controlled for all of the avenues of escape, right? And so actually, going back to this particular example, say you had 10 possible areas that the dog could escape from. If I closed all 10 simultaneously, what can I deduce about the dog's mechanism of escape? What do you guys think?
Is using some window or door.
Yeah, that's right. So, window or door, or one of those 10 things.
Yeah.
Right? Could I tell you which one of those 10 things?
No.
You're shaking your head.
Not
No.
if you're, like,
Yeah.
open each one at a time and see if you get that again.
Yeah, exactly. And so you actually need variation. You need to be able to observe changes in that thing that you're interested in measuring. And without that variation, you actually don't have the ability to do proper identification. Okay. And so what we're going to be doing is we will learn the statistical tools for closing doors, right? But I will say this is just part of the puzzle. In the data generating process, which is thinking about all of the possible mechanisms in here and, like motivating factors for, it could even be, motivating factors for why the dog wants to go outside. You're gonna find that kind of no matter what you do, you will always need to be deriving assumptions about the data generating process, right? So assumptions are inherently necessary for the data generating process, the DGP. And that's because we have to have some idea of how the world works and how the data is generated, right? And Abel made some of these assumptions in doing these tests, which is like closing some of these doors. Because you could think, well, what if dogs could teleport? Or what if the walls in my house were actually just holograms, right? These are like possible explanations for how the dog got outside, but we kind of assume them away, right? These are silly examples, but they are inherent in that identification process that Abel undertook to like just focus on closing all the doors, right? And so that's one important thing to think about, the like context around your particular problem might be a little bit more nuanced than thinking like, oh, I don't have to worry about dogs teleporting or like walking through walls or anything like that, right? All right. Any, yes, questions? Yeah.
What's the difference between like closing the doors one by one and then leaving what you've already closed, and between just closing one at a time, opening that back up, closing the next one, like an elimination time, seeing what you're actually eliminating?
Yeah, so we do have to have some understanding of so this whole thing of the data generating process as like what mechanisms that you're leveraging. So without being too specific about that example, what I'll say is we're going to cover processes, the process of actually identification, which is what you're talking about, like the order of doing things and what it means to be doing, closing all the doors at once versus like one at a time. Yeah, so if you think about like, if you close doors like one at a time, maybe the dog decides to like change the way that they go outside, right? And so we want to be careful about those things and understand that that is something that could happen depending on the process that we take. Yeah.
Okay, so we kind of have to make assumptions just to figure out how to go about identifying.
Yes, exactly. And one of the sort of classic and really helpful ways of thinking about this process is through the use of something known as a causal diagram. Okay, so causal diagrams. So this is a graphical representation of causal relationships. Okay, so what do these look like? So one, you have variables represented by nodes. And two, a causal relationship represented by an arrow from the cause variable to the caused variable. Okay? So basically this looks like this. If you think that x causes y, you'd have your nodes x, y with an arrow going from x to y, denoting the thing that does the effect, I guess, and y, which is the thing that is getting affected in a causal way. Okay? Pretty straightforward. You do have one thing that you do want to make sure to include actually are unobserved variables. It's common to include this. This is something that you often or almost always will want to include in the graph itself. A U, a big U. Yeah, so we actually talked at some point about this example of how when you observe lots of people wearing shorts, you will see that a lot more people are eating ice cream, right? And so if you were to hypothesize that shorts were the thing that caused people to eat ice cream, then you may draw an arrow like this, right? In physical sciences, oftentimes I am able to run an experiment to introduce variation to observe whether there's a cause nor effect. But unfortunately, in a lot of what we do, right, in like social sciences, you are not often at the liberty to run experiments, and instead we would have to rely on observed data in order to do a little bit more sort of complicated procedure of understanding causality. So if I were able to run an experiment in this particular case, I could tell people to wear shorts and then go see if they eat ice cream, right? And if you did that, you would probably observe that that this is not like a real causal relationship. And so maybe I'll get rid of this. And instead what's happening is you've got some kind of effect coming from an unobserved variable that's related to both of these things, right? And so
would temperature be like an unobserved variable?
Yeah. That might be the unobserved variable in this particular model that you would then try and go and maybe get data on that, right? And so this is an example. Maybe I shouldn't use an arrow. Example of a latent variable that causes both of them. Okay. And so, right, temperature. So if it's really hot outside, you might find that that is the thing that causes people to both wear shorts, but to also eat more ice cream. Okay? And if you could if it so happened that you could easily sort of deduce what variable it was that's causing both of them, as in this case, then you could just, like throw that into the model, and then potentially derive some kind of causal relationships between these variables. But oftentimes, you may be kind of at a loss for what unobserved or what latent variable is actually being omitted. And so you want to think about throwing in a lot of variables into a model to try and control for things in certain ways to get at that causal relationship. And the thing that I'll kind of preach here is balance. If you omit too few things, then many things may end up looking causal. And if you omit too much, you might miss the causal variable and misidentify. And that's kind of really where, related to what we were talking about with the data generating process, in the sort of inference world, this part of it becomes as much kind of art as science. You want to develop a defensible hypothesis and assumptions. So I don't know how many people have ever gone to like a really econometric-y like seminar that's full of like economists where they're looking at causal identification. But when that sort of thing happens, oftentimes the economists in the audience, they're not asking really questions about specifics on like model developments or like metrics of like model goodness or anything like that. Really, when you see economists talking about and defending, the idea of a causal relationship being identified, usually it's like centered around like the initial hypotheses and assumptions being made to like structure a model. And that's, it's important to make sure that is defensible if you're working kind of in this area. Okay. Any questions so far? Let's talk about other sorts of variables that might show up. So one is this latent variable, which are kind of your unobserved variables that you will want to include. Another possible variable to think about is known as a moderator. So if I have x going to y, you might have this kind of moderator z. So z modifies the effect of x on y, but is not causally related. So actually this is often not, this is not a good way to represent it, right? Because z going to y would dictate that it is a sort of direct causal relationship. So oftentimes we represent this as something like this instead. Yeah, and so this is your moderator variable. Okay. Can anyone think of an example of a moderator? Yes.
Maybe if we go to the ice cream example again, maybe the causal variable is that it's sunny, and then the moderator could be the temperature. If it's like really hot, it's more likely that this sunny weather will cause more ice cream. Cause more ice cream eating, and if it's not as hot warm, then less.
So you're saying temperature is the moderator?
Yeah, and sunny is the cause for ice cream. Sun is the cause for ice cream eating, and then the temperature is the.
So let me ask. Well, but okay, but so yeah, this is where we have to be careful, right? So if it were not sunny, but it were hot, do you think people would still want to eat ice cream?
But then maybe like sun compared to rain, like if it's raining.
Yeah, no, but this is a very important distinction, right? So the idea is that the moderator variable itself can't be the thing that actually leads to causal outcomes. It has to interact with something essentially. So
Like somebody has like a sweet tooth.
yeah, so if someone has a sweet tooth, but if someone has a sweet tooth, they may still like want ice cream more. I'm a little iffy on that one. Maybe a little bit better. Okay, Christopher.
Going back to the dog example, let's, I guess, say there's a squirrel running around on a tree outside.
Okay.
It's the motivator for the dog to get outside, but it's not the vector through which the dog escapes. Like the squirrel doesn't open any windows, but it's the reason why the dog is getting out.
Yeah, I like it. That's a good one. Yes. I think that qualifies. Yes. Yeah, I like it. Here's another one that I'll give you guys. This example really kind of cemented what a moderator variable is for me personally. So the idea is you have a fertility drug, and the fertility drug has a direct causal effect on someone's ability to get pregnant. Okay? And can anyone think of what the moderator variable would be here? You have to have a uterus, right? Yeah, sorry, I have it, I wrote this incorrectly. Right, it is the interaction of these two.
So the uterus is the actual.
Yeah,
Okay.
yes, the fertility drug is is your moderator variable, I think. Oh, no. I had it right. It was that is right. Yeah. Just because you have a uterus doesn't mean you get pregnant, but that's the moderator that allows you to get pregnant.
But
Yeah.
just because you take a fertility drug also doesn't mean that you get pregnant, right?
Yeah, well, without getting into like too many gory details, like if you're trying to get pregnant, let's say. Yeah.
You know about bird stuff? And bees?
Wait, but I thought you said X and Z don't go to Y. Only X goes to Y. Z has to go to X. And X goes to Z. Then X then can go to Y.
Like this,
Yeah.
you mean? Yeah. Yeah. So, yeah, you should be kind of drawing it like this. So, I guess the idea, just to clarify, because I think I'm like kind of botching this right now. If you're like trying to get pregnant and you are taking the steps necessary to get pregnant, the fertility drug could be a thing that actually causes you to get pregnant, right? But the moderator variable being whether or not you have a uterus. If you don't have a uterus, then that would modify the effect of the fertility drug on your ability to get pregnant, right? And so, yeah, having the uterus is kind of essentially the thing that's kind of like modifying the effect of the drug. Yeah.
I mean, for this instance, like, how do you differentiate between something that is considered a necessary condition of an outcome
Yeah.
versus a correlatory or causational variable?
Yeah.
Like, you have to have a uterus, but it's like that's that's necessary. It's not even about.
Yep.
It's a variable.
Yep.
In the first place that can affect it.
So when you talk about this more generically, when you build a causal diagram, you may have arrows going from like A, B, C, D, and there's this question of like which thing along that chain is the causal thing, right? And the basic idea is it's the last thing that goes to your outcome variable. Because the whole idea is if you are able to break the connection between A, B, C, D, if you were to break the connection going from like B to C, but you could still observe just variation in C, then that's the thing that's causing it. It's not necessarily B going to C that causes B changing to D. I used to have a different example of this in a larger causal model. Let me think if I can remember.
If you remove the moderator variable, can the effect still happen?
Yeah, but you might observe something strange happening with when you remove the moderator, because maybe you would have observed a decreased efficacy of your drug because you've got both like males and females in your sample.
But it doesn't stop entirely.
Yeah, that's right. That's right. Yeah, and that's one of the tricky things about these causal models is sometimes you could get identification right, but the effect is size might be wrong, right?
Could you use that relationship to identify a moderator? If you remove it, the effect still happens, but is altered?
Conceptually, I think the way that you would want to do that is to like control it and observe how the variation in the control of the moderator variable affects the outcome. So you would look at people who, maybe you might look at a subpopulation of people who don't take the fertility drug and you just look at variation in outcome relative to the existence of the moderator variable. And then that would tell you something about the moderator variable effect. Yeah.
Why would we use a moderator variable instead of just adding another constraint?
So I wouldn't actually think of it that way. When you say like adding a constraint, you're kind of like talking about like adding variables and relationships, right? The idea here isn't yet to do with like implementation in terms of like how I would structure models, how I would add or take out variables. Right now, we're just dealing with the like concept of starting to build up causal diagrams in like a logical way. So this has more to do with us making assumptions about how the world works, because I had this caution about balance and developing a defensible hypothesis and assumptions. Actually, the way that a lot of people start to build a model, like a regression model, is to first build the causal diagram, because that's going to inform how to build the model, and it in itself it provides the logic for why you've decided to build the model that way, and it should be like more defensible, right? Because you see the like relationships. So it's not about, at this point, it's not about like building the regression model and adding variables and relationships. It's about just developing a hypothesis of what the relationships are.
So then, based off of building the model,
Yeah.
would then our moderate variables then turn into constraints when we go to like actually?
Yeah.
Okay.
Yes, exactly. Yes.
Is a moderator variable like a candidate for an instrumental variable? Like, is that a way to think about a subset of that, or is that wrong?
Yes. Moderators can be, it is possible for a moderator to be an instrumental variable, but not all moderators are going to be instrumental variables. And the reason for that is, so we're going to talk about instrumental variables later, but an instrumental variable can operate only on the outcome through the variable of interest, right? But a moderator isn't exclusively constrained to operate on just that. It can operate on like other variables as long as it's doing it so indirectly. So yeah, moderator is, instrumental variable is a moderator. Not all moderators are instrumental variables. Yeah. Yes?
I think this is probably stating the obvious, but it seems like best practice to constantly ask what your research question is, right? Because it seems like you could have, like in the dog scenario, you could have dog, escape, squirrel, but depending on what your research question is and what your objective is, what you're trying to figure out, perhaps they could play different roles in the equation, right? But does it depend on what you're asking? Like if you're asking what the motivator is, then that would
Yeah.
right?
So the research question definitely informs, yeah, the research question for sure informs the structure of the model. Yes, that's absolutely true. Okay, give me 1 second here. Is it this one? Wait. So, going back to Ryan, your question. So, I'm trying to remember the whole spiel that I gave about this. So this is an example of a causal diagram. Okay. So, so if we were to just ignore all of this stuff up here for a second, usually when I kind of draw this out the first time, I just do this linkage. So you have frequency of brushing teeth. This can lead to gum disease. Gum disease can lead to an inflammatory immune response, and that can lead to sort of heart disease, right? If you you know, this may cause this, this may cause this, this may cause this, but it's not necessarily this thing that causes this thing, right? And so that would be kind of like saying, if you don't brush your teeth, you're gonna get heart disease. And that can be one sort of causal factor in this chain, but the idea is that like, if you could somehow control for gum disease and control for this, right? Do we still think that frequency of brushing your teeth would lead to heart disease? Probably not, because you've actually controlled for the like elements in this like causal chain, right? So that's kind of the idea behind like thinking about at which point you would actually determine that causal relationship. It's the sort of last thing. And again, the way that we do that is to like break the connection between some variable of interest and our outcome by like controlling for the variation in the downstream pieces of it. Yeah, and if you were to, and I'll just continue on with this particular example, like if you were able to have data, and you would have these variables and data associated with these variables to understand the variation and the relationships between these things. And again, sort of ignoring that stuff, like would we be able to tell the causal relationship between, you know, any one of these guys and heart disease? And the answer would be no, because we have omitted these things. So even without knowing these particular things, right, health consciousness is, that would be the example of like the latent variable that you didn't control for. And there are like plausible explanations for how health consciousness like leads to other types of things that contribute to heart disease, and that without, let's say, controlling for them in some way, you may misattribute things that you're measuring here causing heart disease that are actually should more be attributed to like other factors that you didn't control for. And that's why this idea of like omitted variables is really important when we think about causality. And if you've missed something, then one could always ask the question, well, how do you know that the thing that you were measuring was the thing that caused the outcome as opposed to some other things that you missed, right? Okay. Any questions? Let's take a break for 5 minutes, and we'll get back to it afterwards. Oh, I'll also make a quick announcement that I won't be holding my office hours tomorrow. I have 2 doctor's appointments, so unfortunately, if you need to meet with me, you'll have to schedule, separately. Yeah. And I'll post that on Canvas as well. Hi.
I was able to graph everything that I needed in terms of the difference. But I'm experiencing an issue where my model and my equation all result in NAs, and I'm not sure why. So this is my code where I start in A. I arrange it, I make another data set that I can reduce with, I make a data frame to input things into, and then this is my for loop.
Yeah, I mean, it seems like it can't work. Yeah.
So what's happening?
So when I look at, like, for example, my partial predict D, it's all NAs, and if I look at my model, it is also all NAs. There's no coefficients, there's nothing of substance, and I'm not sure why.
Did you start by dropping everything, or you?
No, it's for loop, and it goes in one row, and I only reduce at the very end. So
Where is
this is my model.
reduced model? Where's that data coming from?
Reduced MAC.
Yeah, where's reduced MAC?
Reduced MAC is the same as Michaela trips, and at least my understanding was that since I'm reducing it, right, I'm going into the next one, I'm dropping it at the very end, that this should still be able to work normally. Does the reduced need to be Michaela trips?
Let me see. So if I run this right now, oh, yes, I see. Okay, I think I know what's happening. Where's reduced model? Okay, where's
Are you looking for MAC? Reduced MAC? That's right.
Sure.
And that
Okay.
one's
Okay, so that one. Okay, and partial predict.d. Okay, watch this.
okay.
Watch closely. If it, hopefully it's not too fast.
I didn't see anything.
Oh, it went too fast. Yeah.
What?
Okay. So I changed the for loop to run once, and reduce MAC and partial predict now have some numbers. Okay.
Okay.
Now I'm gonna run it twice. So how many numbers does this have? 866. Right?
Oh,
And I run it twice, and now it has less. Or well, it should be. I have to reset it. Now it says 865. Let me reset it. Okay, and let me do it three times. And what do you think? How many will it have?
It's gonna be that minus
3.
3.
Yeah, so 864. Okay. So, do you kind of see what's happening?
Is there a mismatch between the partial predict number?
No, you're still good.
Okay.
Your partial predict is still here.
Okay. Number of rows.
So you are asking it to run a model, reduce the number, reduce the size of the thing, and then run it again. And so if you keep reducing till there's till zero,
So
then
I
there's
have to
nothing
make it
there.
stop before 0?
Well, I don't know.
But,
All right.
but that doesn't make sense, because then why would it corrupt everything before it?
What do you mean?
Like, for example, like, if this keeps on going repetitively, right? No, this still has a number, this still has a number. And if it goes all the way to 0 and it can't do it anymore, shouldn't that loop stop instead of just saying that everything has become an A's?
No?
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 Then how are we supposed to go back and find, like,
Well, you're not storing the models that you run through.
oh, I don't have a container? Is that
Oh,
the issue?
yeah, probably. Yes.
So should I just make another data frame and then make the reduced model
Yeah.
refer to the data frame?
Yeah, you could do it that way. There is so if you look in the homework, there should be like some kind of stop condition for like when do you want to run this till?
Oh, 800.
Uh,
800 drops, right?
I don't remember, but yes, something like that.
Because
Let's do this after.
after,
'Cause I
okay.
gotta-
Yeah, thank you. I'm
Yeah.
sorry. Yeah.
Okay. All right, let's continue on. Oh, my battery's dead. All right, well, so much for this. Okay, so talking about balance, one thing that we can think about in simplifying our causal diagrams, here's a couple kind of rules of thumb. Okay, so simplifying your diagram. So one, unimportant. If arrows are tiny / unimportant, you can probably remove them. So that is to say that maybe relationships exist, but the effect is like negligible or has no real bearing on the outcome of things that you are interested in, then maybe who cares, right? So two, if they are redundant, if there are variables that have the same arrows coming in / going out, you can maybe combine them, right? And so yeah, if you have, let me think of an example here. Something like X, Y, A, B, C, D, like this. You might consider these guys to be redundant, and you can combine that. Mediator variables, mediators. So if one variable is only on the graph as a way for one variable to affect another, we have A, B, C, then you can remove it. So maybe this might be, you would be removing B in this case. So to reduce confusion with the earlier example that I gave about brushing your teeth going to heart disease, in that particular example, I was describing it in a way that it isn't a mediator variable, right? Because I was saying that there are other things that might cause gum disease or an inflammation response that you could control, for, or that you could use to control the variation in those observed outcomes. And so brushing your teeth wouldn't be a causal link to heart disease. On the other hand, right, if it were truly the case that that the only thing that affects gum disease and the only thing that affects inflammatory responses are brushing your teeth, right, then those two things in the middle would be mediator variables, and you could get rid of them. And in that case, brushing your teeth really would be the thing that would be causing heart disease, okay? So the really key distinction is it's only there for the purposes of getting an effect of like A through C via B, and that nothing else can go through B. Yeah, and if anything else is going through B, you can't get rid of it. Yes?
I'm not sure I understood your explanation of why brushing your teeth is not a mediator. It seems like it fits the description.
Yeah. In the way that this has been drawn, these two guys would be mediator variables, and we would get rid of them. In which case, there would be a causal link between brushing your teeth and heart disease. Okay. In saying this, I'm sort of contradicting what I was saying earlier, where I was saying that if there are other things that could affect gum disease or inflammatory immune response, and we can control those things to observe variation in here, that would break the causal link between brushing your teeth and heart disease. Okay, so imagine you have another variable here, which is like using mouthwash. Okay, if that existed, then these could not be mediator variables, and we could not come to the conclusion that there is a causal relationship between here and here, directly in that sense. Okay? Okay. And lastly, 4, irrelevance. If it's part of the data generating process, but not relevant to the research question, then remove it. Okay. One last note about the diagrams themselves. Diagrams must be acyclic, which means no loops. None of this works if you have an acyclic diagram. Yeah, because all of the arrows are actually dictating specific relationships. If you have things going around in circles, it breaks everything. So no loops allowed.
What if your situation causes that?
There shouldn't really be situations where that's happening. Yeah. All right. Let's talk about an example. So I want to understand. I want to understand the causal effect of drinking wine on a person's lifespan. And so we would actually call this drinking wine as part of your treatment. And then the lifespan would be the outcome or the effect. Now, going back to my sort of earlier discussion, right? And if this was kind of like a physical sciences type thing where I could just run an experiment, then I could just take a population of people and I could just force them to drink wine and observe how their lifespan would change, right? But we can't do that, and instead we have to rely on observations. But in the observations, and I should say when I run this experiment, we would want to do what's known as like a randomized control trial, right? Because you want to, I'm sure you guys have heard of this before, but you want to randomize it so that there's factors related to certain subgroups of people or subpopulations of people that might have an effect on the outcome, and by randomizing it, you can control or remove those effects because you would have you would think that those same factors that affect the outcome are present in both your control and in the treatment group. Yeah, and so if we could do these experiments, our lives would be a lot easier. The like types of regressions that like the medical community uses are like way simpler than the stuff that we have to do in social sciences, because they don't have to deal with a lot of issues here that may confound a lot of confound our ability to measure these effects, right? And so, without the ability to do randomized control, we rely on observations, and then we have to think about what factors there are that exist out there that may have influences on both the treatment and on the outcome, okay? And so what are some possibilities in terms of things here? We've got, let's say, data about income, about health, and maybe something about like drugs, how much drugs people are taking. Okay, and so we want to, and then obviously we might also have our sort of latent variables. Okay, so here, we want to find all paths. And actually, sorry, before we do this, I need to draw the relationships. Okay, and so we may hypothesize something like this. Okay? And my decision to construct the diagram in this way is based on, right, like my view of the data generating process on my, this is essentially my hypothesis, right? This is informed by my worldview and understanding of like the context around this particular problem, and I've sort of decided to construct the causal diagram in this way. Okay, and so what do we do from here? So here we have to think about, we need to find all ways the treatment in green and outcome, which is the red, variables could be related. Okay. Let me see here. Okay. So the systematic way that we do this is we start at treatment variable, and then follow one of the arrows in/out of treatment to find another variable, follow one of the arrows in/out of that variable, repeat 3 until you find the outcome. And so this would be known as a path or a variable already visited. And that would be a loop, not a path. Which is not allowed, right? So hopefully you never run into that. Otherwise, this doesn't work. And you would just keep drawing loops over and over again. Every time you find a path or loop, you back up one and try a different arrow. Okay? And that's just like a little pseudo algorithm for being able to identify all of the paths to go from treatment to outcome. All right. So let's do that. I can go from wine directly to lifespan. So I've gone from 1, 2, straight into 4, and we've got a path, right? So wine to lifespan. That's 1. We can go from wine down to drugs, drugs to lifespan. Bam, there's another path. So wine to drugs to lifespan. What's another path we could take? We go from wine up to income, over to lifespan. That's another path. So wine. Oop, what am I doing here? Income, lifespan. We can go from wine, income, to our latent variable, to health, to lifespan. Wine, income, health, lifespan. We can do wine through health, through lifespan. Wine, health, through the latent variable, to income, to lifespan. Okay. Does anyone see any other paths to go from wine to lifespan that is not covered in this list? I'll let you guys look at it for a second and tell me if you guys are satisfied with what we have so far. We good? We're good. Okay. So kind of this is like all I did was kind of follow the procedure to generate all of these. So each of these things that I've just written out represents a plausible story that tells us how wine and lifespan may be related. Okay? And any one of these plausible stories could represent the true relationship between treatment and outcome. And not all of them are causal, right? So who can point to a story that would describe the relationship as not being causal? Yes?
I would argue that the influence of income to lifespan is not directly causal because...
This one.
Yeah.
Yeah, okay. And yeah, that's right. There's no arrow that goes from wine to lifespan, right? It's going this way. So can you concoct a story about that particular path? So
Wine expensive, so if you have no income, you can't get wine. Doesn't necessarily mean that you'll live longer or you live shorter, right?
yeah, well, in this case, it's kind of like the richer you are, the more wine someone drinks. We observe there's this relationship from income to wine. We also observe that people who are richer have longer lifespans, right? And so it is income that is causing, these two things to kind of move together, right? And so we could say that this is a plausible explanation, one of the plausible explanations. And I would contend to you, right, that any one of these represents a plausible explanation for these two things kind of moving in a sort of correlated way. Yes?
Does that mean they're linked by causation or correlation?
So depending on which path, right? I'm not saying how we're doing this yet, but depending on which path like is the one that is maybe deemed the most likely in whatever way we do that, right? That would tell us about whether or not relationships are mainly correlational or if they are causal, right? So if I were to deem that drinking lots of wine causes you to do lots of drugs, which causes you to have some decrease in your lifespan, right? There, I may actually be describing a direct causal link between wine and lifespan. But in this other example, we were saying that that may not actually be the case. Like here, for example, health going to wine and lifespan. We are saying that actually, people who are healthy tend to drink less wine. Maybe I don't know the actual relationship. I'm sure this is like kind of debated.
Probably the way around, right?
Yeah, it could be. Who knows? You're really healthy, so you feel like you can drink a lot of wine.
No, I'm saying if you drink more wine, you're less healthy.
Yeah. But in this particular case, we have the arrow going this way, which I'm not saying is right. That's like just the way we decided to like hypothesize the relationship. But sure, yeah. And so, given if we assume that our data generating process is correct, and we've constructed our diagram this way, right? Then the idea here would be this thing of like health causes you to have a certain type of lifespan, and it also causes you to drink some amount of wine, and therefore there's correlations that's related in that way.
So would the income be like an added variable here, if you're just something relevant, kind of? Or how would we interpret income?
Well, so in this case, what you've essentially said is something like, when I control for all of these things, it turns out income isn't the thing that's affecting it. That is the process with which I would arrive to the conclusion that this is the correct path, right? Does that make sense?
Yeah.
Yeah. So, what was I gonna say here? Yeah, so we can once you've kind of set this up, you now have this framework to kind of reduce the diagram to these sets of paths, which are essentially potential hypotheses for you to be checking, and that at the end of the process, when you go through and determine, through your sort of modeling, kind of what you think the relationships are, then you have set yourself up to be able to describe the plausible story related to the results that you're going to find. Okay? And I'll say causal relationships will always flow through your arrows in one direction. Correlations between variables can flow in both directions, right? And so I can actually make inferences about certain things, even if the arrows are going, going in the opposite direction of the arrows. I can make inferences about certain types of relationships and correlations, but causal relationships are only going in one direction, okay? Okay, any questions about this? So amongst all of these different potential pathways, let's talk about this. Let's talk about path types. So a good path is a path that relates to your research question / a path you are trying to identify. A bad path is a path unrelated to your research question. And we really want to obviously focus on the good paths, right? And if our research question in that particular example is having to do with understanding the relationship between wine and lifespan, our outcome, then all of the good paths should have both of those things in there. And if not, then it's probably a bad path. And you should probably get rid of it. Okay. So that's kind of generic ideas of like what you should be including in the paths. And let's now talk about more specific path types. So there's something known as a front door path. This is a path where all arrows point away from treatment. Okay? And a backdoor path this is a path where at least one arrow points towards the treatment. Actually, let's jump over here. So I'm not tall enough. There we go. Front door, back door. Front door, back door. Front door, back door. Back door. Yes. Right. So in this particular example, we've got 6 paths, 2 front door paths, 4 back door paths. Okay. An open path. A path in which there is variation in all variables along a path, with an asterisk being that no variation in any colliders along the path. And I will get back to this in just a moment. A closed path, a path in which there is at least one variable with no variation, asterisk, or a collider with variation. Okay, so why is this important? So let's take an example of a path here. If I look at this guy, income going to wine, income going to lifespan. If you observe variation in wine and lifespan and income, then you have what's known as an open path. If I have no variation in my income, but I do observe variation in wine and lifespan, I have no basis for which to relate wine to lifespan in that path, right? Because income is not changing, and so you don't have an ability to get any information about how that relates to changes in wine and lifespan. That has to be coming from other sources of variation, and so that path is closed to you, right? So this is like closing the door, right? You observe changes in wine, and you observe changes in lifespan, and by closing the door or removing the variation in income, I now have to say that variation that we observe from wine and lifespan can't be coming from income through that particular path. Does that make sense? Yeah.
So I guess just to frame that in one statement, on a closed path, the variable with no variation is not responsible for the outcome.
Yeah. And in fact, like the entire pathway becomes closed.
What does that mean?
It means, so if we forget about that particular path and I'm looking at this path instead, specifically this path, if income has no variation, then this entire pathway is closed, which is to say that
That is not the relationship.
yes, the way in which wine and lifespan are related cannot be through this entire path, okay? And not just that variable. Your entire path is closed. It would be kind of like if the dog had to get through a vent and a door, and you closed the vent, then by default, they couldn't have gotten through the door because they couldn't go through the vent, I guess. Yes, the vent door. Yeah. So we're kind of trying to be systematic about, the formation of the diagram into how you would break the diagram out into all the paths that you're interested in, into how the paths are then useful for you, right? And so if I can close all my paths and just open one pathway, then that will help me determine, right, the causal relationship. Okay. The last thing we'll talk about today, right, so what is this asterisk that I'm talking about? So that is in reference to a collider. So this is a variable along a path if both arrows on either side of it point at it. Okay, so this would be, for example, treatment, and you have A, B, C outcome. So B is the collider variable. Okay. So if you have a path that looks like this, the one thing to note is that this is closed by default. If you control for the collider, the path opens unless you control for another variable in the path. And by control, what we mean is you eliminate the variation, right? And so by default, there's variation happening here. And if you control for that variation, you actually normally, right, if you were to do that in a variable in a different path, you would then close the path. If you eliminate the variation in your collider variable, that actually opens the path. So a little bit counterintuitive. This works the opposite of normal variables in your diagram. And that's because of the way that information flows. Okay. Any questions about that? Okay, I think this is actually going to be a good place for us to stop. And next week, when we pick up again, we are going to show you guys how to leverage the causal diagrams and actually implement real models to try and get at the causal effects of variables. So this is kind of setting the ground stage for understanding all of these relationships and paths and all that, and then we're going to show the implementation in the next lecture. Okay? Any last minute questions about this? Yeah.
Not necessarily about this, but about the project.
Yes.
Where's a good place to start looking for data I'm kind of confounded by like, if I need to start with a topic or start with the right data. It kind of seems like
Topic. Yeah. You should come up with a topic and then try and identify data that is relevant to things that you're interested in working on.
how do you know if it's good data?
I will help you with that.
I don't.
Yeah. Yeah, so if anyone has any questions about the project in reference to, whether the data is enough, whether your idea is like scoped appropriately, you can always come chat with me. Okay?
Thank you.
Yep. Okay, great.